right, good evening. I'd like to welcome everyone to this very special event. My name is Megan Jindrzejczyk. I'm with the MIT Club of Boston. I'm the vice president for the Boston Seminar Series, which is usually throughout the year. We try to have a series of events bringing MIT professors and MIT alums together to talk about the work that they're doing and that the alumni community is supporting. This event we're also having in conjunction with AMITA as part of their Ellen Swallow Richards commemoration event that's been going on all year. And Sarah Simon and Susan Kannenberg are going to talk more about that in a moment, but I'm going to take a few minutes just to say a few words about the MIT Club of Boston. I mentioned we have a lot of events throughout the year, and a variety of types of events. There's an online book club that meets once a month. This month they're talking about the lives of Margaret Thatcher and Angela Merkel. We have a dining club that meets throughout the year, and on the 7th of November, they're going to be having a Portuguese New England clam boil in downtown Boston. It's always a very, very fun event. I hope. Yes. For those who don't know, yes, a clam bake involves lobster. And on the 16th of November, there will be a seminar on designing your retirement. So, AMITA also has some events coming up that I wanted me to mention. I'm sorry, I've forgotten. Oh, tomorrow, actually. Tomorrow is an event on pay equity, civil rights and employment, a candid conversation with MIT alums Kristen Smith and Rob Corbusier. And of course, on Sunday, December 8th, the annual birthday party for Ellen Swallow Richards. The speaker is still to be determined, but it will be on one of Ellen Swallow Richards' favorite topics, water and the environment, food and nutritional sciences, food safety, women in science, and of course, as always, there will be cake and ice cream. And so with that, we will be doing Q&A at the end of the talk. So for those of you who are on Zoom, you can pop your questions at any time into the chat or the Q&A box, and we will, during the Q&A period, we'll read them out in the room. And for people in the room, I'll be passing around the microphone for questions. And last minute reminder, if people could please just silence their cell phones. And I'd like to pass over the mic to Sarah Simon.
Great. I'm going to go stand behind the desk because I want to change this title slide. I'm Sarah Simon, class of 72. I'm a civil engineer. And I have done environmental work all my professional life, so hearing from Susan Solomon is going to be particularly fun. I also did air pollution control work. Let me get this to... Yeah, I better do that as soon as it gets back in the holder here. I just wanted to talk a little bit about AMITA. I'm a past president of AMITA. And with the 150th anniversary of Ellen Swallow's graduation, she didn't become Richards till later, we thought we would do something to honor that and to record the women who had come to MIT through a chair that Emma founded 50 years ago. So she did get a SB from MIT in 1873, and then 50 years ago, the centennial convocation for Ellen's graduation date was set up, and at that centennial, the women who had been working on getting this Ellen Swallow Richards chair going the fund for the chair was announced then. There were only a handful of women on the faculty, especially tenured. So that was the point of us setting up this chair. But Susan Kannenberg is going to tell us a little more because she was involved at the time with some of the discussions. A quick word on AMITA. It was established 125 years ago. And originally we were the MIT Women's Association. AMITA has supported alumni. We've organized programs around interests of alumni, I should say alumni, not alumni. And we have fostered connections with MIT from the women alumni. By the time of Ellen Swallow's death in 1911, nearly 600 women had come through MIT. We actually did a survey back then. So this is at the period when most of the women's colleges were being started, et cetera. A lot of the women who studied science here went out to be professors at Smith and Holyoke. And AMITA does celebrate the legacy and accomplishments of alumni and supports women students and alumni in attaining their fullest potential and achieving their desired impact on the world. And so Susan is one of our, let me go back here then until she gets here. Susan Solomon is one of our speakers, came here as a 5-year Ellen Swallow Richards professor, at which point she now, I'll tell you a little bit about her bio as soon as Susan Kannenberg tells you a little bit more about the way the fund got done. Or I could bring you the mic, either one. I am finished for now. Thank you.
Encumbered with hips and feet and whatnot.
Old hips and feet.
Oh, by cracky. Okay, so I'm just representing the energetic AMITA leaders in 1973, whose courage and commitment, I say, allowed the founding of the Ellen Swallow Richards Chair. I was there, and all I can say is it was, you know, a statement of, you know, confidence in the future. Because, well, I'm sure most of you are aware of what it's like to not be, you know, not know what it's all going to be. Anyway, on behalf of the energetic AMITA leaders in 1973, it was a very, very small group, you know, didn't have a high profile at all. But anyway, the few of us that were there did the best we could, whose courage and commitment allowed the founding of the Ellen Swallow Richards Chair. And I want you to know that in 1973, it was really a high flyer. It was just fantasy land. In celebration of this 150th anniversary of Ellen Swallow's graduation and 50th anniversary of the establishment of the chair, I mean, it sounds so old and so established and so forth, but I can tell you, as somebody that was there, it was most definitely a wild idea. We have to remember what an unusual, brave act the establishment of the chair was back in '73. We celebrated in 1973 the centennial of Ellen Swallow's graduation and kicked off the campaign to fund the chair in her honor, a chair whose purpose was to bring senior women to MIT faculty. Professor Walter Rosenbluth, some of you may remember him, then provost of MIT, whose eponymous chair, I love the chance to use that word at last, I've been waiting for years, is occupied by one of our own Ellen Swallow Richards professors, met with Marjorie Pierce, a leading donor to the chair, and myself to discuss the steps needed to fill the chair. Professor Rosenbluth, does anybody remember him? Okay. God, it's really sad. Anyway, he was a heavy-duty guy. I mean, he was our provost and influential. He was dubious about even having the existence of this chair because of his suspicion that our intended candidates didn't exist. And he actually wanted to fill the chair at home by an incumbent faculty member. I won't say any more because there's no point. Such an action was contrary to its purpose. I mean, those of us who raised the money for the chair and pushed to have it exist, whoever paid for it, was certainly not interested in relieving MIT of a tenure burden by having them take over that chair that we had worked so hard to create. Anyway, Marjorie Pierce and class of 1922, Marjorie and I had our challenge laid out for us right then. Concurrent with the kickoff campaign for the chair's funding in '73, AMITA held a celebratory centennial event featuring exhibits, lectures, dinners, cocktail parties. It was really pretty amazing when you consider that the folks that were involved were a small number of people for sure. The centennial event featured exhibits, lectures, dinners, and cocktail parties. Our MC was President Jerry Wiesner. Anybody remember him? Thank you, at last, who managed the large convocation in Kresge. I should note that AMITA first considered celebrating Ellen Swallow's admission to MIT, which was in 1871. The point is, 2 years makes a great deal of difference. It just does. At that time was, they were going to waive the tuition for the first woman so that if the experiment fell short, MIT could pretend it never happened. Instead, as some people feared, it only encouraged them. The audiences in the past have liked that one. Anyway, I love it, just the nose under the tent theory, I guess. But in 1971, there was absolutely no interest whatsoever. And we tried. Myself, some other people, Dorothy Weeks, class of 1922, some amazing characters indeed. And we tried a situation that was cured just by 2 more years of waiting, and the women's movement, by the way, that had something to do with it. Indeed, in 1973, the chair was finally established and fundraising began for this important goal to bring accomplished women to the faculty. Fundraising for a chair for a woman faculty member, I mean, think of it, this is not like your favorite thing. Certainly the people with the bucks were not, screaming in the halls for this. It was not an easy task, and the slowly growing fund, it was a very slowly growing fund, was a tempting target to many in the MIT world who couldn't abide an unused fund sitting there growing so slowly. So MIT stepped up and found the means to complete the fund, and we were off and running. Happy endings really are great. So that's kind of a nuts and bolts summary of where the Ellen Swallow Fund came from, where the idea of having a professorship to honor Ellen Swallow and all that went with that. In retrospect, it sounds so simple and straightforward and obvious and so on, but I assure you, as living example, or living what's left of what was, in those days, it was not at all obvious that we were going to succeed. There was a little contretemps, which I won't go into, between Jerry and one of our number over the matter of, was it, to whose credit did the women's present go and so on. But in any event, we're here now. We have, MIT is pretty much balanced between men and women. There doesn't seem to be any question of whether there will be women faculty, continue to be women faculty, and all the consequences of all the things that I've mentioned. So let's look forward to the rest of this presentation. Thank you for your attention.
Thank you, Susan, as I introduce another Susan. Susan Solomon came to MIT into the ESR chair in 2012. And I hope you've all read the bio that we had in the event thing. If you look her up on the web, there is plenty of information. I will also say Ellen Swallow Richards, if you look her up on the web, she's all over the place, if you look for her. But when she came, she had been working for the National Oceanographic and Atmospheric Administration, thank you, NOAA, I prefer to say NOAA, and also at the National Center for Atmospheric Research, which any of us in the air business know about, because that's in Boulder, Colorado. But she will talk a little bit about her early history. She was leading a scientific expedition to Antarctica by several years, only a few years after she had acquired her PhD at University of California at Berkeley. And mostly, I know that she has won more than 50 awards, and I lost count trying to read her curriculum vitae, and that was finished. That was written in 2017, so there's been more since then. And she recently wrote a book called Solvable, How We Healed the Earth and How We Can Do It Again. Her book is even in the Unitarian Universalist bookstore, so it's a spiritual thing about the Earth. What can I say? Today she is, after the 5 years in the Ellen Swallow Chair, she is the Leon Geraldine Martin Professor of Environmental Studies at MIT, which was an interesting title to read. I hadn't realized that. I know civil engineers where I came from are now civil and environmental, but she heads the program on oceans and climate in the Department of Earth and Planetary Science. And she also, back in 2014, when she was an ESR professor, was asked by the Vice President of Research to do something about climate and environment, and did found the Environmental Solutions Initiative, which exists today. And it's a major part, it's one of the main pillars of climate work that is being done at MIT. There are a lot of other centers also, but it's a lasting legacy. So, Susan, if you will please give us your knowledge and insights, we're all excited to hear.
Thank you so much. Thank you for that beautiful introduction. And thank you, Susan, for that wonderful historical discussion. I really enjoyed that. I could have listened to you all night. But instead, I'm afraid you'll have to listen to me for a little while. So what I'm going to do tonight is to tell you a little bit about my own current research. I'll also talk about basically the whole story arc of ozone, because I think it's wonderful to have a chance to reflect on how humanity actually did save the ozone layer. And I'm going to show you the evidence now that shows that we are already starting to see the ozone layer begin to recover. I'm not going to talk about my current research. I just don't have time to do that. Some of the things that I'm going to talk about a piece of my current research, but I won't talk about all of it. We do some work on volcanic eruptions and how they affect chemistry and climate. We do some work on climate change in the more sort of classical way, if you want to think of it that way, things like extreme events, their emergence as observable changes. And we do some work on how wildfires affect the stratosphere. I'm not going to have time to do those, but I am going to talk about our own work right now on whether or not the ozone layer is recovering. Let me just say at the outset that I am deeply, deeply honored to have come to MIT as an ESR chair. Ellen Swallow Richards was a remarkable scientist, teacher, and environmental innovator. The more I learned about her over the years, the more impressed I was. You can guess which one she is in this picture of a bunch of faculty, and that's, of course, her. I'm not sure which one she is in this picture. This is this one? Yeah, that. My left or your left? Okay. Yeah, that's what I thought. I thought she was this one. That's what I thought. I thought she was this one.
These were some of her students.
Yeah. So, you know, that's about probably all the women that were at MIT at that time. But, you know, she also was an environmental innovator, particularly as far as clean water goes. Boston became one of the cities with the best water quality earliest because of really her efforts. It's really quite amazing. So I am very, very honored that that I was selected for this chair. Ozone in the atmosphere. I'm sure you've heard all about it. Most people know that it's a form of air pollution, and they also know that that's not where most of the ozone is. If you look at ozone as a function of altitude, most of it is in a layer well above our heads, somewhere between 15 and 25 kilometers. So that is the good ozone that I'll be talking about today. I won't talk at all about air pollution. Ozone is produced by photolysis of atmospheric oxygen, making O atoms, which then recombine with another oxygen molecule and a third body, M, which would usually be nitrogen, to make ozone. And this is a picture of a guy defending his PhD thesis. That man was named Paul Crutzen. And what he did was to come up with the idea that ozone was also getting destroyed by catalytic gas phase cycles. The one he talked about was this reaction involving NO as the initiator, forming NO2, which then reacted with O to make NO. It's catalytic, it goes back up there over and over again, and that's the net of that reaction. So the other thing that you have to think about is transport by atmospheric winds and waves, and what happened were that other gas phase catalytic cycles were later discovered, and particularly one involving chlorine from chlorofluorocarbons made by human beings, which I'll show you in a minute. So why do we care about the layer of ozone in our stratosphere? We wouldn't have life on the planet's surface if we did not have an ozone layer. Life was only able to come out of the oceans and be on land because of the existence of our ozone layer, because it absorbs certain wavelengths of ultraviolet light that are otherwise very damaging to the DNA of animals, plants, human beings. You know this if you've ever been sunburned, and you know, of course, that if you get sunburned too often, you can get skin cancer. You probably also know that too much exposure to ultraviolet will cause cataracts. And so it's very clear that this is dangerous to human beings, also to animals and plants, if you have less ozone in the stratosphere. And that makes this issue personal. That's personal is the first of 3 Ps that I'm going to tell you. My belief is that they are absolutely essential in addressing environmental problems. We do our best job as a humanity when issues are personal to us. And this issue was immediately personal because of the fear of cancer. It just doesn't get much more personal than that. Well, these are the 2 guys who came up with the idea that maybe we had to worry about chlorofluorocarbons or chlorofluoromethanes, CFCs, because these molecules are long-lived. They live anywhere between 50 to 500 years in our atmosphere, and they were increasing in large amounts because every year that you use them, what you had there the year before, is still there with a 50-year lifetime. Almost all of it remains and just builds up and builds up and builds up. And they said, hey, there's a catalytic cycle involved here that would happen like this. The chlorofluorocarbon, like this is CFC11, which is one of the most abundant ones, would react with sunlight. Only when it gets to the stratosphere do you find enough light to break it down, making chlorine atoms. Those chlorine atoms then go on to engage in a catalytic cycle, just like the one that involved nitric oxide. And actually, this guy was a postdoc when he did this work. I already mentioned Crutzen was a graduate student, and the 3 of them, Crutzen, Molina, and Rowland, actually won the Nobel Prize in Chemistry in 1995. So I always tell my students, you got to pick your graduate work and your postdoc really carefully, because you never know when, hey, you might win a Nobel Prize down the line. The other thing you should do is check your page proofs, because you really wouldn't want to win a Nobel Prize for something that has a typographical error actually in the title. I kid you not, that is how it was published in Nature magazine in 1974, but it didn't stop them from getting the Nobel Prize. Everything I've told you so far considers only gas phase molecules, gas phase chemistry, and you want to remember that because I'll come back to it. Well, at the time that Molina and Rowland wrote their paper, which was 1974, remember the date, the use of chlorofluorocarbons was mainly from spray cans, and actually mainly from hairspray and underarm deodorant. So yes, you couldn't have ever have had those. Did you have a beehive hairdo, Susan, ever in the day? Yeah. And so people would spray this stuff on their hair in large amounts, and the stuff. Actually, the chlorofluorocarbons just get the material out the nozzle. They are the propellant. They aren't the material. But they were used in everything from paint to oven cleaner to essentially every spray can around. And what we thought, when I was a graduate student, what we thought was that if we kept using the chlorofluorocarbons and halons, which are compounds containing bromine, which are in fire extinguishers, that they might deplete the ozone layer by about 5 to 10% in 100 years. So a small effect far in the future, a future problem, kind of like the way people used to talk about climate change. And then suddenly, in 1985, everything changed. We weren't talking about 5 to 10% in a century. We're talking about 50% then, and in a place where people never expected to find it, namely the Antarctic. So the Antarctic ozone hole was discovered in 1985. I was 29 years old. I was only a few years past my PhD. And I can't really begin to describe to you how shocked the science community really was. Honestly, I think I'm the luckiest environmental scientist on the planet, because I was young enough to be part of this, and then, years later, I became an Ellen Swallow-Richards Chair. I mean, it just doesn't get any better than that. So the people who discovered this were the British Antarctic Survey. They'd been measuring total ozone at their station right here for many years. It was fairly constant, and then boom, sometime around the late 70s, it just started falling off the map. And it stayed that way. These are the October monthly averages. Remember October, because I'm going to come back to that too. The Japanese station quickly confirmed what they had to say, and so did we. And later on, the satellites also revealed this remarkable ozone hole. So it was a graphic image. It was a hot crisis, and people are much better at solving hot crises than slow crises. We did a pretty good job on, for example, Ebola, and maybe less good of a job on stuff that happens to people slowly, like shingles, for example. Although we're getting much better at shingles. We're just talking about shingles, which is why I mentioned that. But it took many years, and we did Ebola in just a few years. It was easy to understand. There was no need to be a statistician. You can clearly see this just an amazing change. So here's my second P. It was perceptible to people. It was personal, and it was perceptible. You have to wait a while for the third P. At that time, people said, hey, the stratosphere is just a place where gas phase chemistry happens, and there just aren't enough particles for them to matter. It's the gas phase reactions, chemical reactions of free atoms and free radicals by a very famous chemist named Thrush from Cambridge. So that's the kind of stuff that I grew up on as a student, and then all of a sudden this ozone hole came along, and I said, something's got to be special about Antarctica. What could it possibly be? So in 1986, I theorized that what might be happening is this reaction taking place on surfaces, because Antarctica really is the coldest place on Earth. And the stratosphere is so dry that polar stratospheric clouds only form when it's exceedingly cold. They hardly ever form, they do form occasionally in the Arctic, not necessarily every year in the Arctic, but every year in the Antarctic in the winter and spring. So that's why you don't have an ozone hole in the Arctic except in very unusual years. And you have one in the Antarctic, year after year after year. I'll show you some more of that. So the key ingredients then to forming an ozone hole would be man-made chlorine slowly builds up till it gets to the point that it destroys ozone quickly. You have extreme cold and polar stratospheric clouds, and you have sunlight. And I'll show you where the sun comes in a second. So what this paper did was to change the ball game for stratospheric chemistry from being not just gases, but also involving surfaces. And this has been one of the greatest privileges of my life, really, to have worked on this paper. So the way it works is hydrochloric acid and chlorine nitrate, which come from the chlorine in them, comes from the CFCs. They are inert. As long as the chlorine is tied up in those species, then ozone is safe. They don't react together in the gas phase. They do get together on a surface. They make molecular chlorine. This guy, we've now seen that reaction that I theorized in the laboratory by many, many different studies have seen it. And then molecular chlorine reacts with sunlight to form atomic chlorine, and now you're off and running to catalytically destroy ozone. So I like to say that the chlorine is now activated for ozone loss. So you change the chlorine from a reservoir to something that's capable of destroying ozone. It's like the potion in the Dr. Jekyll and Mr. Hyde story. Those clouds really change the nature of the beast. So if you have a typical ozone profile, like what I showed you in the beginning, that gas phase chemistry of Moline and Rowland would just nibble away at the neck of the ozone layer and give you something like a 5% depletion in 100 years with much more chlorine than what we have today. But what the polar stratospheric clouds do is to give you much more ozone destruction with actually the 1980s kind of levels of chlorine and now as well, in the heart of the layer. So that's how you get rid of half the layer. You just can't get rid of more than 5 or 10% if all you do is get rid of it way up there where there isn't very much to begin with. So that's how it changes, and that's the National Ozone Expedition arriving in the Antarctic in August of 1986. It was about minus 40 degrees Celsius, which is also minus 40 degrees Fahrenheit. So if you're ever on Final Jeopardy and they ask at what temperature are they the same, the answer is minus 40. I didn't know that before. People are nodding like they knew that. I'm so impressed. So this is actually not the sun coming up behind me. That's a truck headlight out there. It's very dark this time of year because August is like February in the northern hemisphere, and it's still quite dark in the southern hemisphere over the pole at that time. So I was the head of the expedition of 16 people. I was the only woman, and honestly, those guys were fantastic. They were wonderful friends. It was just a fabulous experience to work with every single one of them. So some of them launched ozone balloons. A group from the University of Wyoming did that. And they saw stuff that looks like this. So if you take a look at ozone in August at the South Pole, it's going to look like the blue line. By the time, and I'm sorry if anybody's colorblind, this should have had different colors. But by the time you get to mid-September, which is this line, boy, it started to get really eaten. And then by the time you get to late September, and then August, it's just astonishing. And you can look at that essentially every year. But you can imagine how we felt in 1986 when we measured this for the first time. It was just amazing. So again, a very perceptible change. I've shown this kind of picture to, fourth graders, and they get it. So, MIT people are like, well, why don't you get on with it and talk about something more complicated, which is fine. But I will point out that the depletion gets pretty much saturated by around early October. The ozone is driven to near zero, which tells you have more chlorine than you need, and I'm going to come back to that later. So one of the things that my group did was spectroscopy. That was really what I was there for. So we took white light from the sun or the moon or the sky. We put it through essentially a prism, slightly more complicated than that, but basically a prism. And had a detector, which at that time was one of the first photodiode arrays. And we actually fingerprinted the signal of chlorine dioxide. So it's an absorber in the visible. It's a very weak absorber, but we were actually able to see it, particularly using moonlight, actually. So that was exciting. This kind of measurement is now made by satellite. I mean, it took me standing out there. I think I have a picture. Yeah. So here we are standing out on the roof with our mirrors, and you go up and do it in the middle of the night to do the moon. I mean, it was really exciting. But it took us a lot of time to get one measurement at one place. They were important because they showed that we had values 100 times bigger than elsewhere. And that was indicative that the chlorine chemistry of Antarctica was unusual, was unique, actually, and probably the cause of the ozone hole. Nowadays, because this kind of measurement is made by satellites, that's one of the reasons I got out of doing this and into analyzing satellite data and other people's data instead, because satellites now, the data sets are immediately available. I mean, it's great, but it means that the room for ground-based measurements has really shifted. So what we now do is more modeling and data analysis. We do a little bit of analysis of things like aircraft data too, but mostly satellite and other stuff. So we measured a host of important chemicals between the different people who were down there. That's those 16 people. We measured CLO by microwave emission, OCLO I already mentioned by visible absorption, NO by infrared absorption, NO2 by visible absorption, we did that also, hydrochloric acid by infrared absorption. So we had multiple independent measurements by different methods of all the suite of chemicals involved in this story. And they all told the same story, that the chlorine was massively perturbed and it was probably what was causing the ozone hole. And that's me again, having the time of my life at 30 years old. DuPont declared it would phase out production of CFCs in 1988, just 2 years later, And that was a pretty amazing moment. In the late, I guess it was 1999, I got the Medal of Science from President Clinton, which was a wonderful honor, but honestly, the best honor was going to Antarctica and doing the work. It was just it's such an amazing place to visit. If you ever get the chance, just go, don't worry about you have time to pack, you'll find something down there, you'll figure it out. It's so great. Okay, so the amount of chlorine that had been in the atmosphere had been increasing up until about the year 2000. And if there had never been a protocol to control the chlorine, it would have just kept skyrocketing. In 1987, and by the way, that's where we would be now. And bear in mind, that's where the ozone hole showed up. So think about that, Many, many times more chlorine would be in the atmosphere today, and we would have had very large ozone losses, particularly actually in the tropics as well as Antarctica, certainly in the Arctic, and also at mid-latitudes. Nowadays at mid-latitudes, we have about a 5 to 10% depletion of the ozone layer. If we had, 3 times, 4 times more chlorine, we would have been up to, 3 or 4 times the 5 to 10%. You can do the math. So that's not what we're doing. We do have the Montreal Protocol. At first, they froze the emissions at then current rates. They said, just don't make any more next year than you made last year. And then slowly, the various countries agreed to phase it out completely. By the time they met, so it's just like the Paris Agreement. They meet over and over again, and they try to agree on bigger and bigger cuts. This didn't take very long. Between 1987 and 1999, all the countries of the world, including China and India, agreed to phase out the production of chlorofluorocarbons. So we're now following very close to the zero emission line, and the ozone hole will probably go away. I hope to make it to the time when there is no ozone hole. My grandmother made it to 101, so I got a chance. It'll probably happen sometime around 2050, 2060. That would be about her age for me. But one of the interesting questions you can ask is, okay, well, we're here. We really are saving the ozone layer. I can show you that from measurements of chlorine, and I will in a few minutes. But can we already prove it now? And that's one of the things that has now occupied a lot of my attention. So in 2011, I decided to come to MIT mainly because I really wanted to, do something else for the last however many years of my career, especially teaching. I really love students, and the MIT students are amazing. And where else would you get to wear wolf ears with a bunch of MIT students? I mean, nowhere else but, MIT. So we had a retreat at Great Wolf Lodge, which was a lot of fun. So are the CFCs declining as expected? I mean, it's just astonishing. Look at how they increased through the 80s and 90s, and then boom, humanity turned the corner on these things. And they are, instead of shooting up as they had been doing, they are coming down slowly because they have lifetimes. This particular one is 55 years, actually. So with a long lifetime, it's going to take a long time to go away, but you can, and it's actually following very close to what it should be doing. You see a tiny bit of cheating going on here, and you can tell there's cheating because the northern hemisphere gets ahead of the southern hemisphere when there's emission going on, because almost all the humans are living in the northern hemisphere. And then it turns the corner, and then they start to converge because nobody is emitting anymore, and then all of a sudden there's divergence, and that was China. It was a mistake. They fixed it, which is great. It was just a company, a rogue company, and now you can see that things are coming together again. It's a fantastic story. So the Chinese were very good, I think, about discovering the problem and fixing the problem. Great. So chlorofluorocarbons are decreasing. We're down to here now. So is the ozone layer recovering as expected? That's what I'm now working on with my students and postdocs. So the question is, there's 3 stages of ozone recovery you can talk about. One is the rate of decline might slow down. The other one is it might get flat instead of worsening. You might call that the ozone is in remission if you continue the health analogy. And the next step would be ozone actually increases in a manner that you can attribute to the halogen decreases. And we'll call that healing or recovery. So it's not obvious from these October averages, really, that at different stations that's happening. One of the things you can do is try to take an average over the whole polar cap and hope that because you're averaging over big areas that you'll average out over these ups and downs, which are partly just caused by motion of, say, this air might move in a little bit toward the pole, and then that station might get a little glimpse of low latitude air, and that causes the ozone to shoot up like it did in that case. So if you averaged over a big region, you might hope to eliminate some of that. You do worry about cases like this. That actually turns out to be a year with a big volcano, and as I mentioned, I continue to work on what volcanoes do. But even if you average over the whole polar cap, and you look at the total amount of ozone in the polar cap region, yeah, you can see it slowing down, and you can see it's in remission, but for October, it's not obvious that it's actually healing. And you can take a look at data from the South Pole, and it's the same thing. October, it's just not completely obvious. There are ups and downs from one year to the other. That's warm years and cold years at the South Pole, which have more or less polar stratospheric clouds. But if you back up and look at September, and this was a really lucky break for me in a paper that I wrote in 2016. So this is MIT work. You can see that even in the coldest years, the lowest years, it looks like you're starting to see some recovery here. And certainly at the South Pole, you're starting to see recovery here. And interestingly enough, September is much less variable than October. That's not a big surprise. September is before the polar region really starts to warm up in the spring. And so it's colder, it's more stable. You can think about that in terms of like how weather is in New England in the spring. It starts to become very unstable. So the October, which would be we all thought that because the ozone depletion was first detected because of that very steep decline in October, that the recovery would be detected in October too. But it's not. It's easier to see in September. And so that was one of the things we showed, and I'm going to show you the reason, which is really cool because it's just basic chemical kinetics. So you can look at the size of the ozone hole, and you can watch it grow. So these are the averages for 1999 to 2008. This is observations. This is a model called WACM. It starts from 0 in August, starts growing in September, reaches its maximum in October of about twice the size of the continental United States, 20 million square kilometers. That's twice the size of the contiguous 48. And then you can watch it begin to go away as you go through the rest of the year. That's because the polar region warms up and ozone-rich air starts flowing into that hole. So if you then look at 2009 to 2014, you might be able to argue there's a little bit smaller hole, but there's enough variability that that's hard to say. But what you can see is that it's starting later, and that's true in the model as well as the data. It's not ramping up as early. It's taking longer to form. When you have a major volcanic eruption, by the way, you get to bigger values and they stay around longer. We've seen that with 2 different volcanoes, and actually the model can reproduce that. So we do understand the chemistry of those volcanoes really quite well. What the volcanoes sort of do, as far as the Antarctic goes, is to increase the surface area because the volcanic particles provide additional surface area, in a sense, to the polar stratospheric clouds. So that's what makes it even more important. But even in the years when you have a big volcano, it still tends to start late. So why is that happening? Simple kinetics, that's all it is. If you look at the chemistry, then you know that the rate of ozone loss is going to be given by the rate of the rate-limiting steps in the catalytic cycles that destroy it, and the 2 that matter are these 2. So that's what controls the rate of loss of ozone. And so you start up here in August, and if you had your maximum amount of chlorine, it would do something like that. With a little bit less chlorine, it starts It's a slower rate of loss. That's all it is. You may still get down to having destroyed all the ozone by the time you get into October, and that is what happens. But it'll take longer to get there. And if you have a lot less chlorine, maybe you'll just barely make it. So one of the things, so that's all it is. That's why September, this period, is a better time to look than October. Obviously, this is a very stylized box model type of thing that I'm showing you just to illustrate. But one of the things we did, which I thought was really fun, is you can ask the question, how long does it take to get to a half an ozone hole? For the let's say instead of getting to 20 million square kilometers, you're only going to get to 10. So that's what we did. Actually, the number is 12. And you can say you want to stay above the value of 12 million square kilometers for at least 3 days. So that's what we looked at. And this is from satellite data. And you can see it's just spectacular, isn't it? It used to happen around mid-September when you talked about the late 80s. And then it got as early as August. And now it's getting later again. Look at that. It's so cool. It's just exactly what it should be doing. And the bottom part of this envelope is actually the coldest years. The top part are the years that are more dynamic. So fundamentally, the chlorine has its biggest effect in September because of simple chemistry, and September is dynamically more stable, and those two things conspire to make September the time to look. And I know that all the figures I just showed you stop in 2015 or so. We have updated that work. My colleague, Kane Stone, was the leader on that, and what he did, he takes it up to 2022. We can include the last couple of years too. It's not going to change the picture. So you can take a look at different levels, different amounts, different sizes, and also different values of how low the ozone has to be to define your hole. The classic number is 220 Dobson units. So ozone less than 220 is the edge of the hole in classic descriptions. But there's nothing magic about classical wisdom. I always tell my students the best thing you can do is question classical wisdom every time you find it. You could say instead of 220, maybe we'll look at 175 or 130. So we're starting to look at the extremes. The parts of the ozone hole where the ozone has really been driven to incredibly low values, you might get down to a number like 130. And so if you look at those, it's even more spectacular. You can really see how clear it is that ozone is starting to recover because you just don't hit those extreme low values anymore. And this is not uncommon. Trends are often more detectable in extremes. Okay, we took a little bit of wonderful time talking about AMITA and Ellen Swallow and all of that great stuff. But I am going to talk a little bit about our very latest work, where now what we're doing is taking a cue from climate change attribution studies. So you're probably familiar with this. If you take a look at the anomalies in temperature, I'm talking about what happens in climate change now, just because we're going to translate this into the ozone world. So you look at temperature anomalies, they might look something like this. The pattern changes a little bit from one year to the other because there's variability. Things like the polar vortex come sweeping down over Boston. That's the kind of variability we're talking about. It goes all the way up into the stratosphere too, by the way. So what you're getting when you look at these is, yes, the world is getting warmer on average, but there's this variable pattern. So you've got a signal of the human fingerprint, which actually looks like this, but it's buried to some extent by noise. And you only get one example of this in the real world, but in the model world, you could actually do this over and over again. So you could run your model 30 times, 50 times, and that's what people do now in climate change studies, so that they can really determine whether or not the human fingerprint is starting to emerge from the noise of variability. You want to look at whether the observed trend pattern is becoming more similar to the expected human fingerprint. Over time, this thing will start to look stronger and stronger as the climate change signal increases, And then, but as you get there, what you need to do is average a whole bunch of model runs to pull it out and see whether or not the signal that you're getting is starting to emerge from that variability. So we want to bring that approach into the world of ozone science. Things seems like a good thing to do because the Nobel Prize in Physics was actually given for this a couple of years ago. So what we're going to do is look at the satellite trend pattern and compare that to models. We're going to look for this region of the polar regions, which we have good satellite data for. And we'll use this period. I'm going to show you a little bit of a later period if I have time in a few minutes. So here's the satellite data as a function of height and month. It's pressure, but let's just call it height. And so you see this, this interesting thing where there's changes up high and they kind of start to work their way down. And then by the time you get to September, remember September? So this is the period from 2005 to 2018 when ozone is, we believe, recovering. And you can see that this trend is positive over a big chunk of it, especially this critical month of September, similar to what I just showed you. If we look at the models, we can take a bunch of different models. So this is one model, an average of 10 runs, and this is an average of lots of different models. And you can see it kind of looks like the data. The pattern looks a lot like the data. The magnitude is a little weaker. That's maybe not too surprising because this is just one run. The real world is only one run, and these are lots of runs. We can find a point if we wanted to, or just take a look at the values at different points, because I just want to kind of emphasize that the data's all over the place, right? I mean, it's got variability from one year to another. Or let's look at this one. It's got variability, but it's clearly got a trend. But you know, that trend is uncertain because of the variability in the fairly short length of record. If we look at the model runs, they're the light lines underneath. You know, there's variability in those too. The multi-model mean is here. That's presumably the force signal. So what you want to do is be able to identify that force signal in the midst of all this variability. And if you've got enough runs of a single model or of multiple models, you can then go look for it. So we'll take our favorite model, and we're just going to take one model, 10 different runs of that model, and here they are. There are many of them look, you know, and here's the data, by the way. So there's the data again, same thing. And many of them look a lot like the model. Many of the model runs look a lot like the data, I mean to say. Some of them look a little bit less like the data, but they all look, you know, something like the data with rare exceptions. So what that's telling you is there's a good probability that a lot of these signals are due to the force signal. And so what we'll now do is identify the fingerprint as being the multi-model mean, or the multi-run mean, I should say, which is this. And we're going to then try to evaluate the variability, which we'll just get from the noise of the 10 different members, the 10 different runs that we had. I'm having to rush through this a little bit because I do want to finish up. But the bottom line is that we can do a pattern matching between the observations and the model, bearing in mind the variability from one run to another over our 10 runs, and we can evaluate the significance over the whole stratosphere and all the months. And we end up being able to conclude that ozone is recovering with 95% confidence. So over time, that signal got stronger and stronger, and it became above 95%, whether you did it with 10 runs of one model or one run of 10 different models, you come up with pretty much the same answer. In the last few years, that's the red line and the blue line here. In the last few years, we've had a major wildfire, and we've had a big eruption from the Hunga Tonga volcano, which is not in these model runs, but it could be. But since it's not in there, that's probably why the signal to noise starts to drop toward the end of the record here. But basically what we're doing then is evaluating the signal to noise based on the covariance between what we see in the signal to noise of the data versus the signal to noise of the model using those 10 different runs to evaluate the noise. Okay, so just quickly, I want to finish up. I want to say something you might not know. A lot of what I just said, you guys probably all know, but what you don't know is that the Montreal Protocol that protected the ozone layer has also been the best thing the world has yet done for global warming. Most people don't know that. And here's how it works. The chlorofluorocarbons and many of their substitutes not only deplete the ozone layer, they also contribute to global warming because they're strong infrared absorbers. They absorb in what's called the atmospheric window of our planet. So they're able to get a lot of radiation, infrared radiation, even though they're relatively small concentrations. So if you take a look at a quantity called global warming potential weighted emissions, which is just a way of weighting different chemicals relative to CO2 as greenhouse gases. So emissions not of just gigatons of CO2, but CO2 equivalents. So here's CO2 itself. It's grown from about 10 gigatons per year up to about 40 gigatons per year now. 10 gigatons in 1961 when Susan graduated to about 40 gigatons now. Here's what happened to the global warming equivalent of the CFC emissions. So by the time we decided to ban them around 1987, most people, I mean, I didn't actually even know this until we made this graph. They were up to about a third of the total global warming potential weighted emission in 1990. But instead of continuing to increase like CO2, they fell off because we stopped emitting them. So if we had continued to emit them, they would have probably done something, this is just an extrapolation of the rate of increase at that time. So CO2 emissions are up here. Here's the world avoided by the Montreal Protocol. It's the difference between this and this is about 11 gigatons of CO2 equivalent per year by 2010. And at that point, it was already 5 to 6 times the Kyoto Protocol target. So the Kyoto Protocol was the predecessor to the Paris Agreement. It's actually comparable to the Paris Agreement 2030 pledges. So actually, getting rid of the CFCs has staved off about a degree of warming that would have otherwise occurred by 2050. A full degree Celsius. It's amazing. But wait, there's more, and it just happened, actually. So here's my third P, practical solutions. Personal, perceptible, practical. That's how we solve problems. The practical solutions were, when it came to, for example, the propellants in aerosol cans, we still have cans. We just don't put CFCs in them to get the material out the nozzle. We usually use hydrocarbons, actually. Blowing agents for styrofoam. We actually still have styrofoam, but we use other compounds to blow it. We actually are getting away from styrofoam altogether and now using much more environmentally friendly things like cardboard. In terms of cleaning solvents, we're moving away from, we have moved away from having CFCs in them. The CFCs were replaced sometimes by compounds as simple as lemon juice and certainly water. The hard one was refrigeration and air conditioning, where the CFCs were initially replaced with HFCs, hydrofluorocarbons. They don't have chlorine in them, they have fluorine, but because they don't have chlorine, they don't deplete ozone, but they are greenhouse gases. And the nations of the world got together in 2016 in Kigali, Rwanda, and decided to add an amendment to the Montreal Protocol to actually phase out the hydrofluorocarbons as well. And when they did that, I thought that's fantastic, but with our divided America today, I'm not sure we're ever going to actually ratify it, but you know what? We did. In 2022, we actually ratified this amendment. So we are we are already phasing these molecules out. We have a binding international agreement on a particular set of greenhouse gases. And if you want to know more about why we don't have a binding international agreement yet on CO2, you could read my book. We have an agreement, but it's only voluntary. The Paris Agreement is not binding legally. So the HFCs have been replaced now with HFOs. They're being replaced increasingly with them, and they will be in the future. So the key points, personal, perceptible, practical, that's how we solve problems the most readily. And I would argue we're past personal and perceptible on climate change. We're now debating what's practical, but that's a huge, huge step forward. I already talked about the lifetimes of these things and the fact that it's a hot crisis. The chemical industry, actually, after an initial period of being against doing anything, came along, and the reason they did, I think, is that they are a technology industry. Their business is making chemicals. Making a different chemical, making HFCs or HFOs instead of CFCs, it wasn't that hard for them to do. It was practical for them to do. And so they were able to be persuaded to make changes. So there's now high confidence at the 95% level that Antarctic ozone is starting to recover. And this has huge benefits for reducing climate change. I did mention the CFCs causing a degree of warming by 2050. I didn't mention that the HFCs, had we not added that amendment, would have caused about 1/3 to 1/2 degree by 2050, we believe. So, it's, again, a pretty significant number if you're trying to avoid 2 degrees. What's next for us? Well, recovery in other places and more work on wildfire chemistry. So thank you for your attention. I'll be happy to take any questions.
So, hi, I'm going to start with a question that's come from online from James Verosco, which is, in your last alumni event, you said you thought there were GHG problems associated with using lots of hydrogen. Time ran out then, so can you please elaborate on what some of the negative consequences are with hydrogen? And also, for those of us who don't know what GHG is, could you please define that?
GHG is greenhouse gas. Sorry if I didn't say that tonight. Hydrogen is not itself an absorber of infrared light, but it indirectly affects other greenhouse gases. One of the ones that it affects is methane, because hydrogen reacts with OH, and OH is the sink for methane. So if you add hydrogen to the atmosphere, you push down the OH a little bit, it actually leads to an increase in methane. And methane, as you probably know, is the number 2 greenhouse gas, the number 2 GHG. So that's the main way that adding hydrogen to the atmosphere does cause some global warming. I don't think I said it was a big problem. Did I say that, really? But what I will say is that it's not, people have the picture that hydrogen is perfectly green. That's a little bit of an exaggeration. The indirect effect on methane is significant. We're actually working on this problem right now in my research group, and we just got a paper accepted on it to really try to quantify that effect. So stay tuned. I think it's going to turn out to be about 1/3 the value of methane itself. So it's a big improvement. If you were going to use hydrogen instead of methane, it would be a win. It would be helpful for climate, but it's not zero. And that confuses people, because people talk about hydrogen being green. It's not, I mean, there's problems with how you make it too. That's another issue, is how dirty is the process that actually makes it. If you make it with renewable energy, which came from the sun, then it's relatively green, except for the effect that I just described, that if it leaks, you're going to get some indirect effect. And of course, they all leak. Methane leaks, hydrogen leaks, all these gases are going to leak when you use them. But you can also make hydrogen in a very dirty way when you make it, say, from methane, and depending on how you do that, it could actually generate even more greenhouse effect. Okay, another question.
Thank you for being here, and thanks for chat. It was really, really great.
Thank you.
You talked a lot about temperature dependence and the role of temperature in terms of forming the whole and the chemistry there, which kind of begs the question: what role does, I guess, a warming planet have with the ozone layer? And would it?
That's a great question. There's bad news on that one, I'm afraid. The planet warms in the lower atmosphere, so the troposphere warms. The stratosphere and mesosphere actually cool. And the reason is that the troposphere is optically relatively thick, so there's reabsorption going on in the infrared. The stratosphere is optically thin in the infrared, so all you have is emission to space going on. It's not getting reabsorbed. And if you have more CO2, it's actually doing more emission. So it cools. So it will only make it worse. I'm sorry, but that's how it came out. It's not a big effect, though. I will say that. I don't think this is going to be a real deal killer for the future of the ozone layer. Probably a bigger issue is actually the fact that as you change the greenhouse gases, you probably change the wave activity in the lower atmosphere, which might make the transport of warmer air into the polar regions a little more effective, which might go the other way. But the bottom line, it's not just a radiation effect, and even if it were, that would be small.
Okay, we have another question from online from Ken Green, who asks, what changes in the 10 runs to change results? At what cost? Why not 10,000 runs?
Great question. You've probably all heard about the idea that when the butterfly flaps its wings, it makes weather, right? So the idea that there's a certain amount of just chaos and random, processes going on that influence day-to-day weather. That is true. So to change the runs, all you have to do is change the initial condition by a tiny amount, and the evolution of the run actually is different. And it's just that truly there is a chaotic component to weather and climate. So you get more or less the same evolution, but not quite. And that's the variability. So that's what all these different 10 runs of the red lines actually are. You just have a tiny change in the beginning.
He also asked why not 10,000 runs?
Oh, 10,000 would be better. They're too expensive. 10 is actually very expensive of this model. That's why it could only do 10. Very, very expensive computer time-wise. It's a big model.
You said that the ozone hole was enabled by the clouds that could form in the cool areas around the poles, and then that layer gets saturated with chlorine. Is there conditions in the rest of the globe to actually have the ozone hole, if we continued to do this, spread globally, or would it just be intensified and stuck down in the polar regions?
We do get some significant ozone loss at lower latitudes, but we don't have those polar stratospheric clouds except under the extreme cold temperatures of the Antarctic. So, does that answer your question? I think it answers your question. The thing that's unique about Antarctica is how cold it is, and you need those extreme cold temperatures to make those polar stratospheric clouds. Oh, I see where you're going. Well, if you have enough chlorine, you can, you can wipe it out everywhere. You don't need the extra push from the polar stratosphere clouds. Yeah, that's a great question. Well, what happens, by the way, at the end of the winter is that this thing does spread out through the whole southern hemisphere. And that's why we have more ozone loss over mid-latitudes, let's say Australia, than we do, say, over the United States. Because there's a significant amount of this that mixes out and actually gets to the rest of the southern hemisphere. But the processes that operate outside of the polar regions are different from what happens in the Arctic and the Antarctic. You still get significant ozone loss, so if you put in enough chlorine, you would get massive ozone loss, yeah. But it's not quite the same chemistry.
Okay, online, I think this question is similar to what you just answered, which was a question about ozone holes, other places than the poles, example, Siberia. So I think you just...
No, actually,
No? Okay.
we have seen a couple of years in the Arctic that were unusually cold and where we have seen something pretty close to an ozone hole in the Arctic. Particularly 2020 was such a year. And we could, imagine that there might be more of them under CO2 increases, which would radiatively cool, as we were just talking about. And that's a concern that people have. But yeah, we have seen a couple of years where you sort of had an ozone hole in the Arctic.
Okay.
Unusually cold years.
One more from online. How many producers of CFC and HCFC compounds was the small number a factor in the success? And also thanks from SoCal for including us.
Yeah, that's a great question too. At its height, there were only probably a few dozen companies worldwide making CFCs. And indeed, the fact that it was relatively few companies, actually even relatively few countries, had a big role to play in why it was possible to, shut it off as a point source. I don't know how many HFC companies there ever were, probably, I don't know, probably not more than 10, but I'm not positive. So yeah, the fact that climate change is obviously a much more pervasive problem. This was a small industry. It was therefore relatively easy to make this change, although people like to remind us that, hey, refrigeration and air conditioning are pretty fundamental. Everybody's got one. So it's not the case that this was some kind of niche product that nobody bought, I mean, in the developed world, most people at least have a refrigerator. Maybe they don't have an air conditioner. But and in the developing world, more and more of them do actually nowadays have refrigerators too. So, but I will say that there are big companies that have been changed because of environmental issues. These may not be, an example of that. This is not an example of that, but if you think about smog and putting catalytic converters on cars, General Motors was the #1 company in the Fortune 500 in 1970 when the Clean Air Act was passed. So we have changed big companies. They were the biggest company in America, and they were forced to make a major change. It can happen when you have a practical solution, like the catalytic converter.
One more quick question. All right.
I was just wondering, you have some wonderful data and some wonderful models. We're entering the age of AI and lots of supercomputers and things like that. If there's one unanswered question you would ask, some of these computers to come, what's the big question to answer?
I'm sorry, what, I don't quite get the question. I missed the question you were making.
Do you have any limitations in the models? Any questions you have unanswered that you'd
Oh.
a super crazy supercomputer to tell you there?
Well, people are trying to apply AI and machine learning in things like climate change, ozone depletion. Honestly, maybe I'm old-fashioned. Probably I am. I have yet to see anybody produce something that told me something that I didn't already know. Because I've been studying this for 40 years, and I have learned a lot about how the ozone layer works. Sure, you can build a machine that can try to correlate everything and figure stuff out. And I've seen a number of examples where people do that, and they learn what I already knew. So I don't know. Maybe they're going to get there, but I'm not seeing it yet. I'm being really old-fashioned here. All right. Thank you so much for your attention. It's great to be with you.
Yes.
Do I need to go back to that last slide or something?
I'd like to, yes, thank you all for coming, and of course, thank you, Professor Solomon, for enlightening us. And we have a small token of appreciation from the MIT Club of Boston.
Thank you.
So, and and I think we're all welcome to stay in the lobby area for a little while longer if people still want to continue the conversation. And again, thank you, and I hope to see you all at some of our future events.
Thank you so much for
Bye.
inviting me.
Thank you.